So let's change gears and talk now about solids. Something we know about all solids is that they're going to have a nice, pretty crystalline structure, and the reason why we know that is because we know that X-rays will diffract through them, and actually something about the X-ray diffraction pattern tells us what type of crystal lattice we're looking at. Now these are all lattices that are kind of repetitive, and first we could look at just a simple cube. We could have a face-centered cubic. We could have a body-centered cubic, or we can have some hexagonal things going on. Keep in mind the important thing about all solids is that we're going to have these nice pretty lattice structures. Let's just take a quick look at the body-centered cubic and the face-centered cubic. Here's kind of another representation. You can see that the face-centered cubic just has an extra atom kind of crammed into the extra space and some more chemical bonds going on right over there. Two examples of some face-centered cubic would be NaCl. We've talked about that one a little bit already, and you can kind of see that it's got a face-centered cubic with kind of some things facing outwards. Another face-centered cubic is going to be diamond, and diamond's kind of interesting. You picture this square or this cube right over here, and then about a quarter of the length down right over here we're going to have another cube and just kind of stuck in there, and then another one, another one, another one. And the one thing to kind of keep in mind is it's really the crystal lattice that determines what we're talking about when we talk about diamond. Diamond is essentially all just carbon. However, the stuff that's inside of your pencil is also just kind of carbon. So really it's just the way that the carbon is arranged. So now let's introduce the concept of energy bands. If we were to consider a solid and it's made up of a whole bunch of atoms, then they're each going to have their own energy levels, and it would look just like the hydrogen atom, or maybe even just a single atom, I should say. But so maybe it would look something with energy levels here, here, and here. However, if you were to start to push these atoms closer and closer and closer together, then we're going to start to get interactions within these atoms, and the wave functions are going to start to distort. And some energy levels are going to be distorted up and some are going to be distorted down. So as we get smaller and smaller and smaller, you're going to start seeing some splitting out of energy levels, especially as we have interactions between all the various atoms. So what was a nice continuous structure becomes more split. Keep in mind the actual separation of atoms is going to be just right here. So what that's going to do is we can talk about how we have some energy bands inside of an atom, and here we're going to have an energy band, and here we're going to have an energy band. Now, probably not surprisingly, the band that is going to be completely empty, and we're going to be talking largely about metals right now, or for a little bit, then we'll talk about insulators and conductors. The one that is completely empty, we're actually going to call that one the conduction band, and then the one that is below that one, we're going to call that one the valence band. Now what the conduction band can kind of do is it can kind of pick up electrons, and sometimes it can even steal some from the valence band. Now let's take a look at insulators, conductors, and then we'll talk about something new called semiconductors. We know that an insulator is going to be a good insulator of electricity, and it's going to be a good thermal insulator as well. Now the insulator is going to have an empty conduction band. We're always going to have that guy. And then it's going to have a valence band right here, so we're kind of looking at 1 and 2, and it's going to have a relatively large energy gap between the two, so it's going to be hard for electrons to jump from the filled valence band out to the conduction band. Now we know that conductors have free electrons, and those free electrons actually live in a partially filled conduction band, and we're going to have the same valence band that we had earlier. Now, we have a creature that's kind of sometimes a conductor and sometimes an insulator, and that's called a semiconductor. A semiconductor looks a lot like an insulator. It's going to have an empty conduction band right on top. It's going to have the filled valence band right down there. However, take a look at this energy gap right here. It's much, much, much smaller than an insulator. And so if we had some electrons inside of this filled valence band, they're far more likely to be able to hop up into this conduction band, and hence the semiconductor will sometimes behave like an insulator and sometimes behave like a conductor. So let's take a look at example 42.5. It turns out that germanium is going to behave very much so like an insulator, or like a insulator. And if we shine some light on it, it's going to start to behave like a conductor. What's up with that? Well, it has a valence gap of 0.06 electron volts, so this guy right over here is going to be 0.067 eV. And if we were to shine some light on there, what we can kind of do is we can liberate some electrons, and they can pop up from the valence band up into the conduction band. It's going to start to behave like a conductor. So we're going to use our good old friend E is equal to hc over lambda to figure out what the maximum wavelength would be. So pretty straightforward. The energy that it's going to take is going to be the 0.67 electron volts, and you can see it's about 1.9 microns. So it's in the infrared part of the spectrum. Visible light photons, shorter wavelength, more energy, will also increase the conductivity of germanium. I just do want to mention very briefly the free electron model of metals. This model assumes that electrons are completely free to move inside the metal. However, there's some infinite potential barriers at the surface. We do know that they can jump off. Something else about this electron model is we figure that the valence electrons are kind of detached from the atom and can move freely within the metal. And so essentially their wave function can extend over many atoms. Now, oftentimes in conductors, or as well as semiconductors and insulators, we're interested in finding out where an electron is. And so fellows by the name of Fermi and Dirac came up with a distribution that's going to give us the probability of finding an electron in any given state. Now, this is going to depend on a couple of things. It's going to depend on temperature. And if we were to consider for a second at absolute zero, and we talked about a conductor, then all of the states are going to be occupied, and it's going to be ground states, and so our probability function right there is going to be 1, 1, 1, 1, 1, 1, 1, 1, all the way up until we hit this thing right over there that's called the Fermi energy. And really all that is it's related to the number of electrons. We know that the electrons are going to be in the lowest state they can, and they can have spin up and spin down. Above this energy state, well, they don't have any temperature, and so we have zero probability of finding them at some higher energy state. However, as we start to increase the temperature, we're giving these electrons some energy, and they've got a chance to be above this Fermi energy right there. So you can convince yourself that it would depend on temperature. And as I said, they came up with this mathematical description of this. So this is going to be a probability. This probability is going to range from 0 to 1, and it's the probability based on finding some energy. And it's going to be related to the energy that an electron has. The Fermi energy, again, depending on the number of electrons. And then this is going to be Boltzmann's constant, and I didn't really talk about that a whole lot in 241, but that's going to be 1.38 times 10 to the negative 23rd joules per molecule degree Kelvin. Or you may see this in electron volts, since we often work in electron volts, and it's actually going to be 8.617 times 10 to the negative 5th electron volts per molecule degree Kelvin. And this is going to be the temperature, and again, that needs to be in Kelvin. And what we can kind of see is if we were to have no temperature, then it's going to go down, drop right there. But as we increase the temperature, so we're going to start to smear this little step well out, and as we increase the temperature, we have higher and higher probabilities out here of getting some higher energy states. Now let's shift gears a little bit and talk about semiconductors. A semiconductor is not going to be a particularly good conductor nor a particularly good insulator, but sometimes it can behave like a conductor and sometimes it can behave like an insulator, and that's really important. How do we change this? Well, we could apply a voltage, we could apply some light. There's a whole bunch of ways where we can make a semiconductor behave more like a conductor or more like an insulator. So how could we make a semiconductor behave like a conductor? Well, we have our standard valence band and our conduction band that we've talked about, and we have a whole bunch of electrons in this valence band. And all we really need to do is we need to give this thing enough energy, again, using a voltage, using some light, any number of ways, and we get these electrons to jump up into the conduction band and partially fill it, and then we have something that behaves like a conductor. Now, these guys right here, they have this energy gap right here, and they're going to have their Fermi energy directly in the middle of this energy gap. So, kind of relative to right here, we could say that the energy that it's going to take to lift an electron from the valence band to the conduction band is going to be equal to the Fermi energy plus the energy gap divided by 2. So there's my Fermi energy, and there's my energy gap divided by 2. So let's take a quick look at example 42.9, where we're going to jump the band gap inside of a semiconductor. And examples of semiconducting materials might be something like silicon, germanium, or something like that. And we can also jump the band gap by messing around with the temperature. So what we're going to do is we're given a couple different band gaps, and what we're going to kind of find is that as we increase the band gap energy, it's going to become harder and harder and harder to jump that band gap. So again, what we're trying to do is pull some electrons, pull them right up, right there. And same thing that I said, the energy is going to be the Fermi energy plus the energy gap divided by 2. And because they gave us the band gaps, it's a little bit more convenient to write this guy kind of like that. And so first, let's take a look at the energy gap of 0.2 eV. And we're going to put this term into an exponent, and so it's going to be equal to the energy gap divided by 2. A little equal sign right over there. So there's the energy gap divided by 2. This is Boltzmann's constant in electron volts, and that's going to be the temperature. It's going to work itself out to be about 3.9. And so we can put this into the Fermi-Dirac distribution and figure out that it's about a 2% chance of jumping that band gap. If we were to increase the temperature, then the exponent changes very, very, very slightly, and it's going to become a 2.3% chance of finding it. So it behaves exactly as we would expect. Increasing the temperature is going to increase the probability of an electron landing in the conduction band. We can increase this to 1 electron volt and so on and so forth, and calculate the probabilities. And as I said, the probabilities get smaller and smaller and smaller as we get larger and larger and larger energy gaps. Now, what happens when an electron jumps the band gap? Well, it's actually going to leave a hole in the valence band. So picture for a second an electron hopping from right there to right there. It left a hole that's actually going to behave like a positively charged particle. And if we were to go ahead and put an electric field on this guy, then what's going to happen is these charged particles are going to start to move, and the positive holes are going to move in this direction, and the negative guys are going to go in that direction. Keep in mind that when I say hole, I mean actually the absence of an electron. There's not actually a positively charged particle right there. However, this can be kind of useful because we could talk about whether we wanted to move positive charges or negative charges by either messing around with the electrons or messing around with the holes. And that's actually going to lead us to two types of semiconductors, N-type, which are going to move the negative charges, and P-type, which is going to move the positively charged holes. What we can actually do is we can add some impurities to our semiconductors to force it to behave more like an N-type or a P-type, and this is actually called doping. Now, with an N-type semiconductor, what we're trying to do is we're trying to move electric charge, and so these guys tend to be really good conductors of electricity. With the P-type, what we're doing is we're actually moving the holes, and so these guys are going to behave a lot more like an insulator. And so that's going to be very, very, very useful. We can dope things with different elements and either make them more like a semiconductor or more like a conductor or more like an insulator, depending on what we want to accomplish. So how do we go about doping? Let's take a closer look. Lance Armstrong did it using blood, but we're not going to be doping like that. If we had a germanium structure just like this, and we were to input an impurity, in this case let's put in arsenic. Arsenic actually has 5 electrons in its outermost shell, and so when it goes into the germanium structure, you can kind of see electron, 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 electron. And we have this extra electron that's kind of a donor electron. And what that kind of does is it gives us this donor level right here. And you can kind of see that this donor level is really, really, really close to the conduction band. And this free electron right there can hop up to the conduction band quite easily, turning this into an N-type semiconductor. Again, one that can behave a lot more like a conductor than an insulator. And we're going to have electrons which we can then move around. If we were to look at the same structure, have some germanium right over here, and we were to put something like gallium inside of it, well, gallium is actually missing an electron right there, and so what it does is it is going to try to steal a hole from one of the nearby germanium, so it's going to, maybe pull that guy just like this, and it has what's called an acceptor hole. And essentially what it's doing is doing the opposite of the n-type. We're creating a p-type, and so we're going to have this guy right over here, and it's going to take one of the germanium electrons, creating an electron hole, and it's not putting that electron up here into the conduction band, so this guy behaves a lot more like an insulator. Also keep in mind for the p-type semiconductors, it's the p, the positive, holes that are kind of doing all the moving of charge here. As I mentioned earlier, a photocell is going to be using semiconductor technology, and essentially what causes the electrons to jump from the valence band to the conduction band is going to be light. We know that light has some energy, and it has to have the right wavelength, and when it comes in, it can pull electrons from the valence band up to the conduction band, and we can have the flow of current. Now let's kind of talk about what happens if we were to put some N material on top of P or some P material on top of N. Suppose we had a really clean P-type material, and we were to just deposit some N material on top of that, then we're going to have what's called a PN junction. And this is going to be really useful because what we can do is we can limit the direction of current that will flow through a circuit. And this is great because you don't get feedback loops and you can't damage electronics. And so right here we have a semiconductor device that is going to be a PN junction, and what this is going to do is we can vary the EMF inside of this circuit, and we can even flip the direction of it, so flip that battery around. And what's going to happen is we're going to have what's called a forward bias, which means we can get a whole lot of current for just a little bit of voltage. Also keep in mind this is definitely not ohmic, it's not a nice linear line. However, if we were to reverse this thing, we're not going to get a whole lot of current for a whole lot of voltage. So we're going to have a very large forward bias, and we're going to have a relatively small reverse bias. So current's going to preferentially flow one direction through this circuit, through this guy. It may have a little teeny tiny bit of current flowing in the backwards direction, but it's very little, and actually that's called the saturation current. Now if we just consider a PN junction in equilibrium, how do these guys work? So no voltage applied to it. We're going to have the P side, and the P side has excess negative charge, and we're going to have the N side, and the N side has excess positive charge, and this is going to be our conduction band and our valence band, and we're going to have the recombination of electrons and holes, and we're going to have some currents right here, and these currents are going to cancel each other out. And so what's going to happen is we're not going to have any current flowing through this guy right here. If we took the same setup and we put it under forward bias conditions, what's going to happen is there's going to be a net electric field in this direction because of that voltage, and we're going to have more current in this direction than we are in this direction, the same down here. So we're going to get a net current kind of going in this direction. If we put a reverse bias condition in, then what's going to happen is we're going to put the electric field in this direction right there, and that's going to push the electrons back to the P side, and they're not going to want to go to the N side. So we can get voltage, large voltage in the forward bias conditions, but not in the reverse bias conditions. Keep in mind that if the bias is, or if this little gap right here is too thin, then the electrons can tunnel from one to the other, and that's just one type of breakdown that we can have inside of a PN junction. Now we can take the PN junction, take a step further, and talk about transistors. Transistors actually are going to have a PNP or a NPN setup, and they're always going to have a base, they're going to have a collector, and they're going to have an emitter, and you'll see that labeled on all the transistors. And what they essentially allow us to do is they allow us to control the flow of current through a system. If you were to consider this setup right here, this one has a reverse bias, and so we're not going to get a whole lot of current over here. However, if we were to give it a forward bias, then we can start to get some current flowing through this guy. So again, if the emitter voltage is 0, we're going to have very small current in this side of the circuit. And what we can then do is we can apply a potential, and that's going to let the holes flow from the emitter to the base. And if we get enough voltage on our collector, then we're going to get a lot of the holes moving into the collector. Now come over here to this setup, and if the voltage is equal to 0, then we're going to have very small current over here. and all the voltage is going to appear at the base collector junction. But as we increase our voltage in our base, then we're going to get more holes going into the collector, getting more current in branch C. We can of course take this technology a little bit further and talk about integrated circuits. And integrated circuits are actually just going to be several layers of material, and then we can kind of etch some things in there and define some current paths, and some really cool stuff can be done with integrated circuits.